Okay, so let's get started. Any questions about the previous sessions?
When
Yeah.
when is deadline of the report?
That's one thing that I don't have an answer for. So how about June 9th? So 2 more days after the presentation. Okay, by the end of the Sunday.
Fine.
Okay, so it might be too harsh to ask the reporter by the day of the presentation. All right, so good. So let's continue. So we started talking about renormalization, and then we've been warming up with a scalar field theory, right? So pi to the cube, we were computing loop diagrams, and we almost done, but now we have to talk about renormalization. So let me tell you where we were. So let me see what we do best for okay, good. So basically, we were computing, things like this. Basically, we were computing amplitude, which was basically, you might say, what am I doing? So we were computing things in the pi to the cube theory, but we sort of have in mind that, we use this sort of diagram like so. So in other words, we have in mind we're looking at some sort of physical processes where these diagrams appear in the T-channel, okay, diagram. So we computed that, and then, so last time we computed this using Pauli-Villars regularization, just so that we have experiences of many different kinds. And then, so calling this coupling to be G, the answer we got was G squared over minus D squared. And then this one has external propagators, so we have this, and then the loop itself, let me finish up, writing the expression, and then we had minus d squared, 30 pi squared, log d squared minus lambda squared, where lambda squared was the fictitious mass of Pauli-Villars coast. Okay, so that was the end of the calculation. And then I told you that the dimension of this coupling for pi to the cube, because Lagrangian should have a dimension of 4, and this thing makes a dimension of 3, this thing has a dimension of 1. So it's actually a dimension of full interaction. And then I told you that, for instance, if you look at the process at a certain energy scale, in this case, for instance, let me call it a energy mu, then you want to normalize this dimension 1 interaction in units of the relevant energy and engineering energy. In this case, therefore, it's going to be called mu g tilde, where g tilde is now a dimensionless coupling in units of, again, the engineering energy scale of interest. Okay, so with this, then we can rewrite this expression. You see now why. And then, but that's one thing. And in each T channel, obviously, T channel where this is minus b squared, which we can call it a, this is negative, we can call it a q squared. Okay, so this is a momentum transfer. Okay, so let me make sure it's a little bit incorrect. Let me fix that. So in T channel, T is negative. For instance, you might have remembered seeing expression like this. If you go to the center of S, right, and this is negative. So actually, minus p squared in this particular physical processes, this is positive. So we're gonna call a minus p squared to be plus q squared, and this is our momentum transfer. So therefore, you can now rewrite this in terms of, so now we can actually rewrite our dimensionless coupling to be squared to be g squared, which is dimension 2, now I can write it q squared. Okay, so let's rewrite this in terms of that dimensionless coupling, as we get with some momentum transfer scale q, we have I times g tilde squared And then combining with these two, you see that you get minus e to the 4, 35 squared log 2 squared over. That's at one loop level. Yes.
그 아까 t가 네거티브를 하셨잖아요.
Yes.
근데 마이너스 t 스퀘어가 포지티브면 t가 포지티브 아니에요?
Well, so that's what I said. What I wrote before was incorrect. That's a rate. So I first wrote the p is equal to minus b squared, and then I wrote it as q squared. Obviously, that is not correct, right? Because one is negative, the other is positive. So sorry, let me correct that. T is negative. That say we agree on that. Okay. So T is negative. So and in fact, you can evaluate this by going to the central mass spectrum. Here P actually is here P is actually 3 momentum sphere, if that's what you were using. Okay. Good. So now we can actually talk about renormalization. So far I just computed it with the regularization, and so then logarithmic divergence sits there. Okay, so how do we do the renormalization? So let's do it quickly. So again, you're gonna do it with own shell or physical perturbation theory. So how do we do it? Well, you pick your renormalization condition. You pick your renormalization condition. Say, I measure this particular process at given energy scale Q. So suppose I define my observable, which is this, or let me just erase I, which I call it to be a G renormalized square. Okay, so that's my observation, which has to be finite and well defined. And then a given theory gives me an expression that it is given by this particular expression. This is finite. This has apparent divergence, and this will also have a UV sensitivity in the Lagrange parameter. And then perturbatively, you can invert this. We have done that. So Lagrange parameter G tilde is now renormalized coupling, and then so this gives me sharp expression that how this Lagrange parameter has to be UV sensitive, precisely this way, so that this particular combination is UV insensitive or UV finite. Okay, so there was a one parameter, and then we made a one observation, one measurement to fix the relationship. So after that, we can make a predictions. So for instance, obviously we can ask is that can I now ask what happens if I measure the same process at different energy scale Q, which is different from Q naught. By the way, obviously Q naught here, you may call it a renormalization scale. So what happened that? Well, I know the prediction given by the theory. So key theory tells me that it should be again this, but with a different Q. So now I know how to rewrite Lagrange parameter G tilde in terms of a renormalized coupling, which is observable, so finite. So first of all, I will have and then here, since my precision of calculation up to G to the 4th, so I'm just gonna keep up to that order. So this I'm just gonna get this. Each of term, each one by one has UV divergences, but if you expect, if you do it correctly, you get finite relationship. So this is completely UV insensitive relation. So relation among observables are UV insensitive. Okay, so we have talked about that. Good. So now let's actually talk about the real thing. So that's going to be another series calculation. Okay, any questions so far? Good, let's do it. So now let's actually do the calculation for QE. Oh, yes.
그 바보 같은 질문일 수 있는데 저 프레딕션이요. Q랑 Q0랑 차이가 크지 않을 때만 이 폼이 발리다는 거죠.
So the question was whether this particular relationship, is valid when this ratio is not that big. That's your question. Yes, for this particular. So if the question is this particular expression is valid when this thing is not too big, yes, that's correct. If you're asking whether I'm allowed to use perturbative field theory to get a relationship with a large enough separation, the answer is naively might say, it breaks down. Because even for a very small thing, I can always take a very large separation that this is as big as that. So it looks like a perturbation theory breaks down. So that's why it's called the large logarithm problem. Okay, just like we have seen for propagator, suppression from the parameters can be overcome by kinematical enhancement effect. So when you have issue with a large logarithm, there's a prescription, by the way. You can overcome that problem. The prescription is that you have to resum entire powers of the logarithms to basically resum it, and then you get what's known as a reknowledging group form of equation, as you will become experts on. Yes. So yes, this particular expression you have to take with a grain of salt, but there is a way of overcoming even with a large separation in terms of reknowledging group. Okay, any other question? All right. So this sounds like you picked the right topic to present. So let's do vacuum polarization. So we're gonna literally not take the question directly. We're gonna take fermion, derivative some mass, and then, as you know, fermion for the derivative, and this with factor. And in case we need to talk about particular charge, we have to insert the Q there. Okay. And then let me remind you a photon propagator because it will become relevant very soon. So if you have a photon propagator, let me say it at tree level. So I'm just drawing a tree level propagator. In momentum space, we wrote it as I pi mu p. So it has a massless pole with I epsilon prescription to ensure a time ordering, as we talked about. That there's a G mu nu. C, mu. The reason why I'm writing this again is to just mention, because it will come up very soon. Sorry, it will come up very soon that this C dependence is a gauge fixing condition dependence, and we talked about the fact that in any observable computation, the second term dependence should drop out, right? Because I can choose different to C. Nevertheless, any observable should be independent of choices to C. So any observable calculation, the second term must drop out. And one of the ways we have seen, for instance, is that as soon as I attach this photon line to conserve the current, as it should be, right? That's how we even started the building of the theory of photon. Like what kind of thing it can possibly couple to? We show it should be a conserved current, and you see that if you sandwich this between the current, conserved current, and this P mu dot J mu is literally the equation for conservation of current, so this term never appears. Okay? So remember that, because it will come back very soon. Okay. So with that, now we will jump into actual calculation. All right, so let me erase this part. Now that looks like propagator in Feynman gauge, which also we will use all the time for today's calculation. So we're talking about vacuum polarization. The physics is that if you have electric field, then vacuum knows how to pop out a fermion pair in this case. So it polarizes momentarily, and then it comes back. So this is the diagram we want to compute. It's the momentum. And if I call a loop momentum to be K, and that should be what? K minus. Okay. So let me call the entire thing to be I times pi mu. This is the correctness to the Boltzmann propagator. Well, so let me just put 2 to say that whatever it is this 2-point function. Okay. So you ready? Okay, we have to do this calculation. So first of all, there's a fermion loop, so let me write it 1 minus f to the f, 1 minus 1 to the f. So that's just to tell you that this comes from the fermion loop, minus psi. I have 2 vertices, so I have minus IE square from the vertex. Yes. The electron is the minus, so I have minus. Okay, so then I have integral over the momenta, so d for k. I have 2 propagators, which are fermionic propagators. But let me first write down the denominator, which is k minus p squared minus m squared, the one of the electron or proton, whichever way you want to use it, and then k squared minus m squared for the other propagator. So I'm not going to put in a I epsilon for now. Okay, now I have to write down the numerator. The numerator, as we learned, for fermion loop is a trace. So let's start from here. As you learn for fermion, you have to reverse the fermion fluid, the charged fluid, and write down the relevant factors. So if this is the mu, this is nu, I have a gamma mu here. And then there's that propagator, denominator part. This is this, matching with that. And then I hit the gamma nu, and then I come back with k slash plus m. And then as usual, there's I for each of the propagators, I will have I to the square. So this is the quantity we want to compute. Okay. Good. So can I just write down the answer? Magically, I just write down the answer and then discuss. That will save a lot of. But let's go through, because this time, so we have gone through hard cutoff calculation, and then we have seen Pauli-Villard's regularization, and this one we'll do it with a dimensional regularization called Dean rank. Okay, so therefore now you're experiencing all best examples of regularization. Okay, and there's another reason why we want to do that. Anyway, so let's do it. So first of all, yes, the numerator first. So let's just tackle that thing, which you should know. So there's a 1, 2 gamma matrices. So there's another gamma matrix here, another gamma matrix is here. So in principle, this will include 2 gamma matrices times m squared term, and then possible some 3 gamma matrices, and then 4 gamma matrices, right? And then you had an exercise in case you have done it right now. If not, well, do it. So 2, we can do it. Any odd number of gammas to give you 0 answer. And then there's also a formula for 4 gammas. There's 4 G metric minus another metric contraction plus metric. Well, it's just nu plus sigma. So this is nu mu nu plus sigma mu rho mu sigma, mu sigma, mu. Okay, bring it. So therefore, you should be able to just compute the entire numerator. So then numerator becomes something which I will write down later. Well, numerator becomes okay. Numerator, if you do it 4 times, because everybody has a 4 in it, p mu p nu minus p nu. What did I say? P mu k nu and then p nu k nu. So this is symmetrized, and you want to see. And then there is a 2 times k mu k nu, and then there is something that is proportional to the method. It's a k squared plus k times p plus this. All right, so this is the total numerator. Okay, explicit computation, nothing mysterious. Let's continue. So that's not the hardest part. That's just one of the part. Now, what do you want to do? Well, you have 2 factors of a propagator, right? Eventually, you want to do the weak rotation. I told you, if in this picture, it's hard, right? There's the poles are distributed random here and there. You may not be able to rotate. So you have to do final propagation. So you learn. Okay, so you should be able to write this A times B as follows. If you do it, this thing becomes okay. So this thing becomes, well, first of all, whatever, the plus minus, and you work it out here, and then I told you numerator. So if you do everything, you should get 0 to 1 dx, the final propagation, and d for k. You should definitely work it out all of this, by the way. This minus, let's just say delta, and then numerator, where delta is m squared minus x, 1 minus x. Okay, good. Yes.
Is numerator tensor?
Good. Yes, because I have not contracted external legs to polarization or anything, so it actually depends on the beginning. Okay. In fact, that's why I also have. Another question. Okay, so I just combine. Now, what do you do? Well, now you want to call this to be your new parameter, new integration variable, k. So k prime first, and then you drop the prime, as usual. Okay. So if you do it, then you get the following. You get the following. So this I have to write because I have to explain things. Let's see if I can manage to write all this expression. Okay, I can do it. I can do it. So therefore, whenever you see k, you have to write it as new variable k plus xp, right? That's what you have to do. Is there a question?
네.
Okay, just surprised that I'm gonna do it. Good. Good. You see, I figured out a way. So this numerator function, wow, very good. This is a function of k and p, right? So now numerator function should be very good. K plus xp, p m, and then k squared minus delta plus epsilon. Done. Okay, good. Let's see. It was. Okay, so now, what do we do? Well, you compute it, but before doing that, let's be clever. So this thing has a lot of terms, but we can organize these complicated terms as follows. So this thing, numerator k plus xb, em can be organized as some term which is proportional to like k. Okay, so here I'm agnostic about the tensor indices, Lorentz indices for now. And then you will have another term, which is p squared, m squared, and the p squared metric. So this is dimension 2 object. Okay, and then there is another term, also a function of external momentum and mass, and then p mu mu. So no matter what, how complicated the expression is, this always can be, organized in terms of these three independent thing. So let's see what I mean by that. Slightly more in detail. So for instance, now whenever you see chat, you have to look at it as a k plus x. Okay, k plus xb, boy, k plus xb squared, and then you know what I'm talking about. So now if you look at this, so first of all, this term is like p nu, p mu, k nu, right? So this is the term which is a linear in loop momentum. So that's what I meant by this term. Okay, and also this one has a p nu, k mu, and so on. So that's that term. And then this term also contains p mu, p nu. Right? So it's a product of two p nu, p nu. That's what I meant by this delta 2 term. And then this thing will have therefore k nu, k nu. So there you might say, okay, there's another term which is k nu, k nu. So let me keep it for now because I did not explain that. Where is it? Where was that? Okay, and then this one also has a mixed term like k mu, p nu that also falls into the first delta 0, and then p mu, p nu, which is the delta 2 term. And then there's a sigma mu, g mu nu, and then there's a whole bunch of terms, k squared, p squared, mixed term, and so on and so forth. Okay, which you can always organize in terms of the term that looks like this. Okay, well, at this point I should have said, so let me put deltas, because I'm going to use the delta itself for other means. And then principally in this case, this should also be a function of t squared. And then the delta 2 in principle now, because this is integrand rather than integrated quantity. Is that clear what I'm saying so far? Good. Now, one thing that I was going to say about the second term is as follows. So now we are doing a momentum integral, right? Loop momentum integral. And then just based on Lorentz invariance tensorial structure, which this is symmetric under the exchange of mu and nu. Okay, once you finish the integration over k, obviously this should render something that is independent of k's. So based on Lorentz structure, the only thing that is possibly can be is actually something that is proportional to g mu nu. And then since it's quadratic in k, it's a k squared. And then by taking contraction with respect to g mu nu, you can actually show that this should be equal to 1/4 or 1/d if you're doing in d-dimensional contraction. Is that clear what I'm saying? So here I use the fact that, so take this, which is some prefactor times that, and then if you contract with respect to g mu nu, and then g mu nu is traced in the d-dimensional delta function, sort of like Kronecker delta, which is d. I use that fact to derive a prefactor. Okay? So the point here is that the term, which is proportional to k mu, k nu, is also falling into the category of the g mu nu term. That's what I'm saying. So after that, we have three kind of term. A term that is terms that are linear in loop momentum. B, which the term that is proportional to the metric. C, terms that are proportional to p nu, p mu, p nu. Now the claim here is that terms that looks like this are all 0. So to see that, let's first clean up. Okay, why is that? Well, it's because of this. So for instance, you're doing a d-dimensional momentum integral, like so. And then suppose you're doing an integral which is linear in k times arbitrary function, which is an even function of k squared. Okay? So this is even, and then you integrate over the entire region limit in the k. So if you do k goes to minus k, change the variable, this is equal to minus of the same thing. Hence it is 0. In fact, not only a term that is a linear in k, but any odd powers of k, you should get, yes.
I think it should be, it can depend on the dimension of the dimension d, I think. So my question is that the equation is valid in even dimension d equals 4. But
What, not sure if I either understand or agree. So here I'm imagining that I already have a minus infinity to infinity integrals, dk1, k, d.
so if you change the sign of k
Yeah.
and the total.
Oh, you pick up the minus sign from here.
Yes.
Thanks. Okay, I think you're right. Good.
Oh, there's no problem, I think, because
Yeah, because if it is a linear, I think this is always true because you're only flipping one of them, like particular direction specified by view direction. But in general, I agree. So if I want to establish the result which is valid for arbitrary odd powers of k, then it'll depend on the dimension d. And in the case of even dimension, then you don't get extra minus sign from the measure part. Hence, any odd powers of k, you should get 0 answer. Good. Yes. Okay. So going back to here, so we were computing this. So we are cleaning up. So basically, any term that is linear in k, we can drop it. So we're gonna keep these two. On the other hand, we are lazy, so we don't want to actually do all the math. But the second thing we want to talk about is this. So the entire pi mu nu 2 p's, which is this integral that we are about to do, we can decompose. Therefore, we can decompose as something of this and then something of that. So I can decompose it as a now delta 0, which not only depends on the external momentum and mass, because I have done the loop integral, which I haven't, but we will show. We will do it. And then something that's proportional to the metric. And then whatever the term that is proportional to P mu. So this is nothing different from this claim. So basically, I drop this. Suppose I have done the actual integration, which is horrendous, but suppose we have done it. So structure wise, you should always take this one. Okay. Now, what we are going to do strategically is the following. For the moment, we're going to drop this term. Okay. Why is that? So here's our strategy. First, we note the following statement. So first, let's ask, what does this delta 1 and delta 1 and delta 2 function do if we include those in the correction of a photon propagator? So we're going to do this. Let's sort this out first. As I told you, in principle, you can resum this, which I will demonstrate if I have time today. If not, let's just look at these two. So if I do this in Feynman gauge, where I take the C to be 1 for a tree-level propagator, so then I have minus I G mu nu over P squares. That's the leading piece. And then from second term, I get G mu alpha P square. And then I have I mu 2 t, which is loop correction. And then, oh, sorry, I have the alpha beta. And then I have another external propagator, which is this switch. And then in principle, we can have a lot of more terms to do. Okay, so they're like, the second term is product of the external propagator, loop part, and then external propagator with the proper construction of Lorentz indices. That's all I have done it. So what is this? So let's actually look at it. If you just plug in this expression, okay? If you literally plug in this expression, let me save some time by just writing down what you should get. So if you do it, you should get the following answer. Minus I, as you would expect from tree level propagator structure, and then you get 1 plus delta 1 g mu nu, and then delta 2 mu over t. Okay, so if you just do the math, you should get this. And let's ask ourselves, what does this mean? First of all, what that means is that sigma 2 doesn't seem to be physical, because at the end of the day, it's just reproducing or reintroducing what you have called like sigma dependent term previously at tree level. And we know that in any physical observables, this particular second term would not appear. Yes.
So you said that if we choice design properly, we can cancel out this effect. Am I right?
So that particular statement is not incorrect, but I'll be careful because we're gonna pick a particular trace of C, and then we're gonna do the computation, right? So we already made a choice at tree level, and then we're doing computation. As we know, otherwise, there's this issue of non-invertibility, blah blah blah. We have talked about. So it's not like I'm gonna make a choice of that to get rid of it. Even if I make a wrong choice according to what you're trying to say, then I might have this term period, and it's not be cancelled by any choice of C. Even then, we know it's okay because this term will never appear in the physical observable calculation. Okay, so at the end of the day, therefore, this particular second delta 2 term, which is proportional to the P mu Q nu, it will end up with a non-physical pieces in the final expression. So we're gonna drop it from the calculation. And then we will spend the time to understand the physical meaning of the first term, which will eventually be related to renormalization of charge in QE. So that's first common. But second common, you might say, oh, still, I'm not comfortable just blindly dropping the second term. If that was the case, in fact, P mu term can be either, directly computed. So that's always possible. Okay? Meaning, forget all this fancy argument, compute it. Just do it. You can do it. Or can be, determined from word identity. So what I mean by the second, so this first is should be clear, it's just computed, okay? The second thing, what I meant was that if you remember, if you had any matrix element, and then if you had external photon line with this, and then you know that if you replace it with momenta, multiply any photon involving matrix element, that should be 0. In the current discussion, what that means is that if you contracted with the 6 loop induced quantity should be 0. So once we finish the computation of this, as I will demonstrate, this term can be immediately fixed and determined without a single calculation. Okay, by just demanding that. Okay, so that's how we are going to organize our computation. Any questions? Good. So yes.
It seems like the one identity just fix the X, the value of X.
you said it seems like word identity fixes the
Very
CC at group level. I think what it should be is that, so this is true regardless. Like this is true regardless of a gauge fixing condition.
I think it should be.
Yeah, because this is a physical statement.
Oh, it's confusing.
Yes, exactly. Now, I think if you actually compute it with arbitrary c without choosing any number, then you will see a lot of expression with the c's floating around here and there. Nevertheless, at this level, all those c terms cancel out, and then you should get this. This is the case. So I think it's a constructive exercise to do that. Even if this thing has a lot of c's in it, it should still fulfill this condition. And then there should be fine, if you wish, translation among the c terms such that this is still says. Okay, so this is how I feel two things can be reconciled. Any other question? Yes.
저희 루머의 사태에서 KU가 저런 식으로 바뀌고 능력함에 들어가서
Yes.
브란트에서 이제 사라진 거가 중요한 것 같은데
Yes.
저기서 G뮤로 K스퀘어로 바뀌려면 K에 대한 능력 개념도 없고 인티그랄도 안 사라지지 않나요? 상수적으로 기여를 할 수가 있습니다.
Sorry. Here you mean?
그 아래 KU가
Yes.
바뀌어서 결과적으로는 어디에 포함돼서 사라지려고 이렇게 나왔습니다.
Yes. Okay. What I said was that the general expression for numerator will have something that is tensorially proportional to G mu nu, and then the only K dependence comes as a K square. And then something tensorially only P mu P nu, and then K dependence only comes as a K square. Tensorially, this thing have many different structures, like a K mu, P nu. So now it has explicit Lorentz indices with it. But it can also have like K dot P with times like K square dependent term. Okay, so and then tensorial structure can have G mu nu, for instance. This will also be 0 because I can write everything as a K alpha P alpha. At the end of the day, I can apply what I said here. Okay, so that will also be 0. The statement regarding K nu was that this, okay, by symmetry is always identical to this at the level of integration, that this should be counted as a G mu nu term. That's what I will say. Did I answer your question, or you still have a question? Okay, good. All right, so with that, therefore, my strategy today is that, so we're going to just focus on this term, having in mind that this can be fixed at the end of the day by the word identity, and then we're just going to compute this up. Okay. So with that comment made, now let me write down the expression that we need to compute. Okay, good. So once you apply all of what I said, nicely organized, then the integration you have to do is this one. Apply more counterpolation, introduce. Okay. And then it's the K square, they introduce delta. Okay, so let me do my search. Ready? See, I'm writing this in 40, literally just for pedagogy. Otherwise, I could have written the expression for D dimension already, but here we go. I'm writing it. Okay, so this is what we need to compute. And then the logic is plus P mu P the term, which we will fix at the end of the calculation. Okay, so this is the term that is only proportional to G mu nu, as we talked about. Now, before I actually rewrite this in terms of G mu nu, let's actually check the degree of divergence. So what is the let's call the superficial degree of divergence, meaning like how badly this is divergent. Okay, naively. So let's check. So here you have a k to the fourth from the measure. Here you have a k to the fourth. They cancels, right? And then on top of it, you have a k squared here, k squared here. So naively, this looks divergent as badly as lambda squared. If I call lambda to be my UV cutoff scale. Okay, so this is quadratically divergent. Obviously, in principle, whenever a given quantity can be, as divergent as the quadratically, in principle, you can expect that everything below can also appear. Okay, so starting from quadratic, linear, logarithmic, and finiteness, in principle, can appear. Okay, so this is superficial degree divergence, and we know that we have to therefore regularize this computation. And in fact, at the end of the day, we should not get these divergences. Okay, and we will only get logarithmic divergence. So let me just quickly argue that and then just jump into the calculation. Okay, why am I saying that? First of all, what does that mean that if I have this divergence? So what is the dimension of this pi mu nu object? What is the mass dimension of this pi mu nu? This is dimension 2 quantity, right? This is a correction to this. So naively, it is this piece. So whatever that multiplies a nu or a nu, so I call that to be pi mu nu. So this is dimension 2 quantity, right? And that's why we see that it can even be formally at least can be quadratically divergent even. Now, if pi mu nu included a quadratic divergence, so let's actually ask that what does that even mean? What that means is the following: there's a lambda square G mu nu, forgetting all the prefactors. What that means is that even though at a tree level, we started out with a what? Massless photon. This is like giving a cutoff scale dependent photon mass as if. That's what I'm saying. So if there were quadratic actual divergences, which is physical, that implies that radiative correction or loop correction somehow generating a photon mass. We should ask therefore, does that make sense or not? Right? And we know that photon mass being 0 is controlled by the fact that there's a gauge invariance. And the gauge invariance was controlled by the fact that we want to talk about manifestly local Lorentz invariant and unitary description of massless spin 1 particle. In other words, what I'm saying here is that masslessness of this thing was already put in by hand, which should be protected by sacred principles such as locality, unitary, Lorentz invariance. And this old fancy thing was encapsulated in a single word called gauge invariance. And gauge invariance means that you can never have a photon mass turned on, whatever you do, if you're using manifestly gauge invariant quantum field theory. So that's the way I argue that such a thing cannot appear. You can ask yourself, what if, nevertheless, I do have this term appearing? What does that mean? What that means is that you have computed this loop diagram that for QED that has U1 gauge invariance using a cutoff regulator, which actually is not gauge invariant. So if you use by mistake UV regularization, which does not respect the gauge invariance, then in principle, this modeling of UV physics, which is a regularization, can induce all possible terms, which is not consistent with infrared gauge invariance. So you could generate that by accident if you use non-gauge invariant UV regularization. Okay, and that will be connected to all this discussion. So therefore, if I do things correctly, meaning if I do compute things correctly, meaning if I model the UV physics in a way that it respects gauge invariance, then I know that such calculation should never generate the quadratic divergence. And I should expect only logarithmic, which I will show. Yes.
My question is that why can we cannot see the lambda further?
Linear, that you can see from by the fact that by tensor structure, there's nothing you can put it into to be consistent. Okay, so this is by power counting, you cannot have.
So also the lambda square term cannot be appear because due to the Maslow's condition of the
Yes, gauge invariance. So if I use gauge invariant regulator, then such a quadratic divergence will not and should not appear. All right, let's continue. So we want to regularize it in a gauge invariant way, and so we're going to do it using a dimensional regularization. Yeah.
So question. The meaning of the lambda square divergence means that we cannot use the hard momentum curve regularization.
That's correct.
We cannot use.
You cannot use it.
Oh.
Yeah. Yes. So even though we talked about like, you know, at the end of the day, calculation should be independent of regularization choice. But there are some, in a sense, you know, for instance, if you do the gravity calculation and you pick a regularization that maximally break all diffeomorphism, then you will get all weird term appearing, because that is, you know, remnant or artifact of choosing wrong regularization. Okay, so let's do it using DIM-REG. So the idea of DIM-REG is the following. So basic idea is simple. To say, suppose you have integration that you have to do, it has this form. Okay, so this. So now you know that this is logarithmically divergent, right? However, if you replace the dimension with the sum d, such that now d is slightly less than 4, then you have more powers in k in the denominator than the numerator. You expect it should be unified. Okay, so that's the idea of a DIM-REG basically. Yeah, although this should work out for power divergence as well somehow. So taking this as a simple idea, we're going to replace this with d now, and then the second term, as I talked about, can be replaced with 1 over d k squared g. Okay, so this is the thing that we want to compute now. Good. So now, actually, let me use this space because then I don't have to write all once from again. Let's use this. No, so previously there were 2 times k nu k nu. And then k nu I replaced with the d k squared over d because I'm doing the d dimension. G mu. That's what I said. Okay.
I think
Yes, it is the same thing. Okay, so now you see this thing has 2 pieces basically. Okay, so the first piece that is common on this side. The first piece is 2 over d minus 1 k squared d mu. So that's the first piece. And then the second piece is x minus x squared m squared g mu. And then obviously there's p mu term that we're going to fix. So here we need to know how to do two sorts of integration. One, which is proportional to k squared in the numerator and then denominator. And then this thing is, excuse me, k squared to the 0th power. Okay, so then we need to know how to do the computation. And then it was, I think, last lecture that I show you how to do this general integral. We have actually walked through step by step how to do this integral. R is for the minus delta plus epsilon the S. So since we have learned how to do this calculation, this we can now read it off. Okay, provided you learn how to do the calculation. So it is a lot of term, but there's a formula, general formula that I derived. So if you do it, then you should get the following answer. Now, I mu 2 b is this. If you do it step by step, over 2 m naught. Okay, so that big expression collapses to this plus e mu. Okay, good. So we're almost there, at least in terms of computing things. So at this point, I need to correct two things about this expression. Okay, one is obviously I'm going to determine this term now, and second, I have another more important fix I have to do. So let me just do it first. So we are doing physics now in D space and dimension, as we have talked about. So we are doing physics in D space and dimension. So what does that mean? So Lagrangian was f squared. I'm just writing so that I have something to look. Sidebar and side. So now this is D dimension, right? Because I'm doing it in D space and dimension. And so that means that the photon field dimension, this has two derivatives. So D minus 2, this is quadratic in photon field, so I divide by 2. So that's dimension of A. So and here, from here, dimension of psi, this has a 1 derivative, so D minus 1 over 2. That's dimension of psi. So now here, dimension of E is D minus, dimension of a photon minus 2 times dimension of fermion field. So if you do it, just plug in the math, you should get the following answer. It should be 4 minus D over 2. What it means is that in a space and dimension D, which is different from 4, then the electric charge or electric photon coupling is not anymore dimensionless coupling. Okay? So now it has a dimension with it. You start carrying positive dimension if you go to the dimension less than 4, for instance. So since we want to continue to use the dimensionless coupling, then we're going to write the electric charge or electric coupling to be now balanced with a dimension of mass to the that power. We talked about this already. And then E. And E is, to me, is still a dimensionless object. So this is still dimensionless by balancing with this. Okay? I already explained to you one instance of this thing, right? We talked about cubic coupling G. So I write it as in units of a relevant engineering dimension mu times G tilde previously. Remember that. So let me recall you. So if this thing had a dimension of 1 previously, I wrote it as mu, whatever the engineering dimension of that thing, times G tilde, where G tilde was dimensions. So I'll do exactly the same thing here, nothing different. Okay, so that's the first fix I have to do. The second fix. So now how we're gonna fix the P mu P nu term. So once again, I have to fix it by demanding word identity. And everything else is, you see, momentum independent, right? Oh, so sorry, this thing has a momentum. However, just because, as you know, this thing satisfies that. And we talked about this indeed is proportional to the projection operator onto the transverse mode, right? So this unique combination is only way to come in this expression so that the P mu P nu term can participate. Okay, so the random appearance of a P squared dependent term, this is proportional P nu P nu, would not satisfy this for arbitrary P nu. So therefore, what I'm arguing here is that if you think about it, to be clear, this thing literally just replace with P nu in edited. Okay, that's the first fix. Second fix, because of the first thing I talked about, there should be mu to the 4 minus d, because not e squared rather than d. Okay, so that is the two fixes that I can do, and that's the expression we're talking about. So that's the regularized vacuum polarization EQE. Okay, so now it's time for talk about physics and equations. Yes.
In this case, d is usually not an integer, right?
Not yet.
Not yet.
Not yet. But eventually you want to come back home, right? You don't want to play.
Yeah, that's right.
So I'm gonna take now continuation to d equal to 4 soon. But if you're doing naively, you will get a craziness.
And
So
is this space Minkowski or Euclidean?
okay, so far we have already continued to the Euclidean space. So this is like Euclidean d dimensions. Yes. So in order to do that computation, where we had to do another continuation before here, and then do the computation. But you see, but Minkowski versus Euclidean, at least it doesn't care. At least the dimension doesn't care whether it's Euclidean versus Minkowski. In other words, even if we now talk about Euclidean versus Minkowski, the number d can be this, will be this. Another question. Okay, so for now, let's take this expression and then make sense of it. In order to make sense of that, now I'm about to take a limit where this goes to 4. But the way I do it is I take d to be, I parameterize 4 minus epsilon. Okay? So I start from a dimension slightly less than 4. And then I gotta take epsilon goes to 0. And then let's see what happens if I do that. Okay. So this thing has several factors that depend on the d. So there is a gamma factor, there's that, and there's this. So I'm just gonna collect all these 3 factors together and work out first. Okay? So here I will have d over 2. Well, let me first work out the easy one first. Gamma 2 minus d over 2 is gamma of what? Epsilon over 2. Okay, and then this thing is equal to 2 over epsilon minus e. This is order epsilon. And this thing was 0.5772. There's some name, Euler Mascherani constant. I wrote that explicitly last time. Okay, this is how this thing is divergent. Okay, now this is singular. And then let me collect the rest of pieces. So I have That's 1, 2. I have mu to the 4 minus d, and then 4 pi to the d over 2. And then I have delta to the d2 minus d over 2. So let's first knock out this expression. Okay, so these two are all the d dependent pieces, so I'm just going to work that first. So this thing is equal to 4 pi squared. If I factor out, then this becomes 4 pi times u squared over d to the entire 2 minus d over 2. So basically, I noticed the fact that 2 minus d over 2 is epsilon over 2. Okay, so I want to write everything as in powers of 2 minus d over 2. Okay, so then therefore I want to subtract by 2 and then multiply by 2. So that's that factor. I have done it. And I notice this is the square of the powers I have written there. Good? Good. And this is again just epsilon over 2. Good. So now what do you do? Well, if you have some number to the epsilon, and then you want to have some sort of expansion in epsilon expansion, the way you do is that you notice that e to the log is 1. Right? So e to the log is always 1, so you just apply that thing. And this becomes e to the epsilon times log of a. So now this is e to the small stuff, provided this is finite, which is finite here. So I get 1 plus epsilon log of a. Therefore, this thing becomes 1 over 16 pi squared, it's from that. And the entire piece now becomes 1 plus. Instead of just epsilon, I have to have epsilon over 2. So I have epsilon over 2, log of the entire stuff. 4 pi u squared over L plus or epsilon squared. All right, good. So a quick comment about 16 pi squared. This is famous, one loop factor. So in other words, if you do research in somewhere where loop matters for you, then you often have to do naive dimensional analysis. And you don't want to compute things, including factors of I, 4 pi, and so on. You just want to check how big the quantity is. So in that case, whenever you see some one loop, you start with okay, so this goes like 1 over 16 pi squared and something. Okay, and that's that. You might say, wow, okay, that's not very convincing because this was after long calculation. How would I know that this is a generic factor? Well, this generic factor is because since we are doing the 4-dimensional quantum field theory, we always do this. So that thing always comes with 2 pi to the 4 from this 2 pi factors. And then there is an angular integration to do. Okay, so they always give me either 2 or just pi squared. Remember, 4-dimensional sphere is 2 pi squared. Okay, I'm not taking responsibility of the factors of 2. So if you look at it, that's that. Okay, so this at least combination of 2 precision of factor of 2 will appear somewhere. Okay, so that's that. Now, okay, so so we have this. So we're gonna combine now this with that. Let's do it. Okay, so let's combine here. Should I erase? Be ready to yell at me. Okay? And I was about to just erase without thinking. Just like stop. Instead, I have to redo everything. Okay, so therefore, let's combine all the d-dependent pieces here. There. Okay. So then I have the following. Instead of writing everything, so the gamma factor gives me 2 over epsilon minus plus over epsilon. And then the rest of the piece will gives me 1 over 16 pi square. And then that thing. So 1 plus epsilon over 2 log 4 pi mu square divided by delta plus epsilon square. So now let's expand. So this is 1 over 16 pi square. And then the leading piece is 2 over epsilon. Remember, I'm doing expansion in powers of epsilon, right? So which is singular. Let's do 0th order in epsilon, which means that I have to collide that with that and with that. Okay, so that gives me minus this plus log of 4 pi mu square delta. And then, so that's therefore this entire thing is over epsilon to the 0. And then higher order. But now higher order doesn't matter because at the end of the calculation, I'm gonna take epsilon goes to 0 limit. Okay, once I know how to regularize and how to renormalize. Okay, so this particular epsilon to the 0th order term can be combined as log of 4 pi, which was there, and then I can just exponentiate this guy, e to the minus this mu square divided by delta. Okay, why is this good? If you don't like, you can write this entire thing instead as, okay, if you somehow mentally enjoys seeing instead of this sort of expression, you are more than welcome to carry around all of that. Okay? And just one benefit of just combining this and then call the entire combination to be something else. To simplify the expression. So you have to write slightly less. Let's just call everything to be this. U tilde square. I just redefine what I meant by a scale when the electric charge is written in a dimensional distance. Okay? Let me say a little bit more about this, though. So now this is a regularized quantity, and then entire UV divergence is captured by this stuff. Okay, because this is a singular. Now, and this is the momentum independent finite piece. This is momentum dependent, which is crucial. Okay, delta has a p square in it. Okay, this is physical. This is a finite. And we have talked about if you have a loop calculation done and there is a random finite constant, those are never a physical quantity. For instance, if you subtract one observation made at specific scale with another measurement made at another scale, any independent piece will just drop out. In that sense, this is unphysical. It doesn't matter whether it's just absorbed in terms of renormalization scale view, calling a different scale utility. Okay, which I have done. Good. So okay, so that's probably all I can say today. And so basically, we have totally, completely computed this in a regularized way. Okay, so if you plug in this, that's the expression which is regularized, and now we are ready to talk about physics next time. Okay, so probably I should wait until next time.